Welcome back, everybody. We're pleased to have Jessica Fintzen, whose title is on the first slide here. So take it away.
Okay, thank you very much. Thank you very much for the invitation to speak at this conference, which is a big honor. First of all, I'd like to encourage everyone to turn on your camera if you feel comfortable to do so, so that I can actually see some faces and so that it looks a bit more like an actual conference. Great. And I should say I particularly encourage the grad students to turn on the camera because I read that grad students are encouraged to attend these talks as well. I opened the chat, but I can't promise that I see everything during the talk. So my talk is about how to get from representation of p-adic groups to congruences of automorphic forms. And one idea of this conference is that we should highlight how Peter Scholz's influences mathematics. And so this talk is about how a tiny remark in a paper by Peter Scholz actually led to some interesting theory. And so I like to begin by showing you the remark. I don't expect that you necessarily understand all the words in there, but afterwards I'll walk you through it. But I want to begin with the remark so that you can keep this in the back of your mind. So here's the remark in one of Peter's paper. It says, one can deduce from this corollary, a corollary that I didn't copy here, the existence of Galois representations for Hilbert modular forms, which are nowhere discrete series, assuming only its existence for forms which are discrete series at a prime p. Thus, this provides an alternative argument to Taylor's construction of these Galois representations. And that's the part I highlight, that's what the talk is about, it seems reasonable to expect that one could do a similar argument in the compact unitary case, providing an alternative to the construction of Galois representations of Shin and Genevieve-Harris by reducing directly to the representations constructed by Harris-Taylor. And so that's what the talk is about, to actually say, yes, one can do that. It's not just reasonable to expect, but it's actually true. So let me begin with the setup. So for this talk, curly G denotes a connected reductive group over the rational numbers, for simplicity, the rational numbers, such that the R points are compact, mod center. So what are these? So for example, we can take the units in a quaternion algebra such that the R points are the Hamiltonians, real quaternions. So these quaternions, and we call we have a basis consisting of 1, I, j, and k, and then we have these relations that I squared equals k equals j squared equals k squared equals -1, and the same for the product ijk. So that's a perfect example. We can also look at, for example, definite unitary groups. So unitary groups of signature n0, so they are compact at infinity as well. And so then I want to denote by A, the adults. So that's just the restricted product over QL for running through all the primes times the real numbers. So it's a product, except that for all but finitely many places, we lie actually inside the L. And I choose a prime number P, which I fix throughout this talk. And I fix a group U upper P, which is a compact open subgroup away from P. So it's a compact open subgroup of the restricted product of G of QLs. So for example, if we work with the quaternion algebra, with the quaternions, then this group here will be at most places, it will be just GL2, and we want our compact open subgroup to be GL2 of ZL, the integers for almost all primes. And then at the prime P, we also fix a compact open subgroup, whichever you like. So for example, you can choose also GL2 of ZP inside GL2 of QP if you want. And that then allows us to define algebraic automorphic forms. What are algebraic automorphic forms? These are just functions on this double coset. So this is G of the adults mod out on one side by G of Q, and on the other side, we mod out by this compact open subgroup, and we mod out by the connected parts of the real points. And so this set here is just a finite set, and we map it to ZP. So in other words, this here is just a ZP module to some rank n. So it's not too difficult a priori. So that's what algebraic automorphic forms are. And then the result, the first theorem, which is joint work with Shin, and that's what is generalizing Peter Scholz's work, is the following in wake terms. It says that algebraic automorphic forms, arbitrary algebraic automorphic forms, are congruent mod p to the m for any integer m you like, any positive integer m, to some automorphic form that is particularly nice, which is an automorphic form that is so-called supercast at p. I'll go into this later. For now, just think of supercast at p being particularly nice because that allows us to use it for global applications. And so this was done by Peter Schultz in the special case that we actually work with a quaternion algebra. And we generalize this now to much more general reductive groups. And so why is this a theorem that we might be interested in? Because of the application, for example, that we, in sloppy terms, may assume that an automorphic form is supercuspidal at a prime t. So what does it actually mean? So for example, if we want to study the global Langlands correspondence, say for GLN, the idea of the global Langlands correspondence is that we start with some nice automorphic representation of GLN. So representation of GLN of the adults of some number field. And we assume that this automorphic representation is essentially square integrable at some prime. Whatever this means, it's something that's actually implied by it being supercuspidal. So in other words, we start with an automorphic form that is particularly nice in the sense that it's supercuspidal at some prime. And then attached to this, through the work of Clausel from 1991 and later Harris and Taylor proved more properties about this, is the Galois representation with QP bar coefficients. So that's the idea of the global Langlands correspondence. But of course, we don't really want to assume that these automorphic forms are particularly nice. And so as a result of this theorem 1, we can actually remove this assumption here. So we can remove the assumption that they are particularly nice, that the automorphic forms is supercuspidal at a prime, basically by saying it's congruent to an arbitrary one. Arbitrary ones are congruent to these nice ones, and that's how we construct Galois representations. And I should also say that Pashkunas and Emmett, based on a work by Emerton and Pashkunas, used similar, slightly different techniques to also remove that in the case of GLN. But the work with Sorgushin has now the advantage that this can hopefully be applied in a much more general setting. And I should also say, in the case of GLN, this is nothing new. This has been proved earlier by Sorgushin himself and Clausel, Harris, Labesse, and Genevieve Harris using very intricate geometric methods. So in the case of GLN, we are not proving anything new. But the nice thing about our result, there are two things. One is that we don't use this geometric method, the complicated geometric methods, but we use only local theory, which I'm going to explain throughout this talk. So we use local methods. And the other advantage is that our results hold in a much more general setting. So the hope is that we can use these results to prove similar results than for other groups. So to push the global Langlands correspondence beyond the case of GLN and to reach other groups as well. And so let me just post again the remark I started with by Peter Schultz. So that's essentially what the yellow remark was about, to obtain this global Langlands correspondence just using these congruences instead of the geometric methods, the complicated geometric methods that he quoted before. So that's the big picture. That's what I like to talk about. And today I want to give you an idea of how we can prove these congruences using the representation theory of p-adic groups, so how this enters the picture. So I will first make the statement a bit more precise about the congruences of algebraic automorphic forms, because I so far gave you only a vague statement. And then I'll tell you a bit about the background of representations of p-adic groups, and in the end, how everything fits together. All right, so I already defined for you algebraic automorphic forms. There's a second kind of algebraic automorphic forms that we like to work with. And for this, I have to introduce the ring AM. A sub M is this polynomial rings where we mod out by this polynomial. So what is this? So this here is just 1 minus t to the p to the m divided by 1 minus t. So that means, in other words, this ring is, we take ZP and we adjoin all the non-trivial roots of p to the m's roots of unity. So that's what it is. And we want to look at, before I say, we want to look at automorphic forms with these coefficients And why are we interested in this ring? We're interested in this ring because if you take this ring and mod out 1 minus t, let's see what you get. So modding out 1 minus t means that all these t's here become 1. So this whole sum becomes p to the m. So that means we obtain the ring ZP mod p to the m. So that means we have this congruence here between modding out the ring AM by 1 minus t and modding out the ring ZP by p to the m. And that's the type of congruences we are looking for. Actually, we want to construct congruences between arbitrary algebraic automorphic forms mod p to the m with particularly nice algebraic automorphic forms. And for this, we choose the ring AM. And we want to ensure that they are then supercast at a prime p. So in order to define algebraic automorphic forms with these AM coefficients, I like to take a representation of my group UP of this compact open subgroup on this ring AM. So in the end, what will happen is just that this representation will be just scalar multiplication. So it's a rather easy representation. And I assume that this representation is trivial on some open subgroups. So it's a smooth representation. In other words, it factors through some finite quotient. It's not too difficult. And then we can define the algebraic automorphic forms with AM coefficients. Again, functions on the double coset, but this time we don't mod out by U upper P because this U upper P, this compact open subgroup of G of QP, this should act via the sigma. So an element UP on the right, element U lower P of UP, should get should transform this function via this sigma of U sub P or sigma of U sub P inverse for technical reasons. So it's again functions on the double coset, but this time U lower P acts via this sigma. And so that's the definition. And now the theorem, the precise statement is the following. We assume that P is greater than the Coxeter number of G. Coxeter number of G is some number here. Don't worry too much about that. It's just for technical reasons and it shouldn't be there. Then the statement is there exist explicitly constructed compact open subgroup UPMs inside G of QP with an action on this ring AM so that we can define the automorphic forms with AM coefficients such that we have this congruence between arbitrary algebraic automorphic forms and these automorphic forms with AM coefficients. So far that's rather easy to achieve because all we can do is just say let sigma act trivial, because if this sigma action is trivial, these are just functions also on the double coset. And we saw already that AM mod 1 minus, so we saw already that if we mod out, oops, here, AM by 1 minus t, that this is isomorphic to ZP mod p to the. The difficult part now arises that from the fact that I said we want these automorphic forms on the right-hand side to be particularly nice. And so that's the third part. Let me first read it and then explain it. So we want that if pi is an automorphic representation of G of the adults, so representation of the adults that contributes to the space of automorphic forms, then it should be particularly nice. So what does it mean for an automorphic form to contribute to this space here? So this space is a space of functions. If we tensor up to QP bar, it's a space of functions with coefficients in QP. And we can act on it by the adults via right translation. This way we obtain a much larger space because it's not preserved. We obtain a much larger space. We obtain a representation of G of the adults. And our automorphic form should be a sub-representation of this representation, should occur in there. So that's what it means for an automorphic form pi to occur in the space of automorphic forms. So pi is now a representation of G of the adults. So it can be written as a representation of all these GQLs, so the components pi L, tensored with some infinite component. And now we want that the component at P at the prime P, this pi sub P, is a supercast representation of G of QP. And I'll say in a moment what it means to be supercast, but this is what I mean by sufficiently nice, because that allows us actually to use, for example, the Jackie-Langlands correspondence and to use geometric methods in that setting that are easier. And then the last condition that I want our peers to satisfy is that these U sub P's, these compact open subgroups, U sub PM, should be a decreasing sequence of subgroups that are normal inside each other. And they should become smaller and smaller and smaller. So they should form a basis of open neighborhoods of the identity. Why do I want that? It's just so that we can actually work with all algebraic automorphic forms of arbitrary level, because that's this UPM is what the level is. All right, so that's the statement. And this is actually enough of, so in rough terms, this means arbitrary algebraic automorphic forms are congruent to those that are particularly nice. And as an application, we get what I've shown you on previous slides. I should also mention that the condition I should also mention first that actually we don't just get a congruence of automorphic forms, we also want the Hecker algebra actions to work out nicely, because that's what you use in applications. And I should mention that Bizarre-Plessis showed in an appendix to our paper how to actually remove the assumption on the prime p, but without an explicit construction, just by using some more abstract arguments from Harishchandra. But we hope that we can actually remove this assumption here in general, and also get an explicit construction which allows us then to know about the Langlands parameters, for example, or to use that we know how these representations look like for other applications. All right, so that's the statement, the global statements about algebraic automorphic forms. In order to prove it, I want to move to the local representation theory next and tell you about p-adic groups. Let me see, are there any questions at this point? All right. Perfect. So then let's move on to the representations of p-adic groups. So the setting now is that we want F to be a finite extension of QP or the normal series or a finite field. For our application, take F to be QP in the end. O should be a ring of integers with a maximal ideal P, and the residue field is FQ. And then G should be a connected reductive group over our field. So for example, think of GLN or SLN or SO and the matrices that preserve an inner product or that preserve a symplectic form and have determinant 1. So for example, in the special case that Peter Scholz worked with, he was working with SL2. But we will work in a much more general setting later. And so then what are these supercast representations that I have been talking about? They are so nice. The supercast representations, one way to define them is saying these are the building blocks of all representations. What are all representations? By all representation, I mean those that are smooth and complex. So these are representations with complex coefficients, or QR-bar coefficients, if you like, where you ignore the topology. And smooth means that the stabilizer of every vector is some open subgroup, so a rather large subgroup fixes it. And these are the representations that occur, for example, when we look at the local components of automorphic forms. And so what do I mean by building blocks? I mean all irreducible representation can be embedded into the parabolic induction of some supercast representation. And the supercast ones are those that cannot be embedded into a proper parabolic induction. So these are the building blocks if we want to construct everything. Another way to describe them is to say that these are the representations whose matrix coefficients are compactly supported mod center, which is why they are so helpful for global applications and why they move through the local through the Jackie-Langlands correspondence. All right, so these are the nice representations we want to study. And there's a folklore conjecture that all these representations arise as follows. First, you construct a representation of a compact mod center subgroup of your p-adic group. So for example, of SLN-ZP inside SLN-QP. And then the second step is that you build the representation via compact induction. So a well-known procedure to start with a representation of K tilde and move it to a representation of G. And you see already the philosophy in here is that we want to study compact subgroups and the representations of them to get supercast representations. And that's what's really helpful in the end for the global application where we had this UP, we knew how this compact open subgroup UP acted, and we want to deduce from there that we work with supercast representations. All right, so that's the folklore conjecture, and that's what we will find helpful for applications. But what do we actually know? So we know that this conjecture is true via some explicit constructions, for example, in the case of GLN, in particular, the case of GL2. This was the work here started more than 50 years ago. Moy and Howard did a lot of important work and was finished by Bushnell and Kutzke like 30 years ago. So that has been around for some time. We also know the classical groups, so fixed points of an involution, if the prime p is not equal to 2. And we know how to deal with inner forms of GLN. So for example, the units in the division algebra. That has been done by Stevens and by and by Stevens respectively. Classical groups was done by Sean Stevens, inner forms by Seychelles and Stevens around 15 years ago. And so for today's application, I want to really work with all reductive groups in as general setting as possible. So let me tell you what do we know more general in the setting. So in the more general setting, it started with work of Moy and Prasad in the 90s, and they defined an invariant, which I call a depth, which can be 0 or a positive real number. And I want to draw a picture of what we know by drawing the prime number p in that direction, because some results depend on what our prime number p is. And so Moy and Prasad and Morris, roughly around the same time, they showed how to construct all these depth 0 representations. They roughly correspond to representations of finite groups of Lie type. But since I said that we want to study automorphic forms of algebraic automorphic forms of arbitrary level, we actually are interested in going deeper down, because the depth is somehow the deeper down you go on the filtration. So what's the depth? The depth, okay, let me restart the sentence. What is the depth? We know that a representation is smooth, means that each vector is fixed by some compact open subgroup. And so what Moy and Prasad did is they defined a filtration of our group by compact open subgroups that are getting smaller and smaller and smaller. And so the depth is just the notion, how far do we have to go down this filtration until we get fixed vectors. And since we want to study algebraic automorphic form of arbitrary level, so where we have small congruent subgroups, we want to be really small in this filtration. So we want to actually look at representations that have small depth, that have high depth, so that we go down into the filtration to have small subgroups. And so that work was, one of the first works was done by Jeff Adler in 1998 and then generalized by JKU in 2001. And they construct a lot of representations. So I marked them here by dots. These are all representations. And JKU's construction is the construction that's the most general we know up to today. And that's actually the construction that Sorgushin and I have been using to construct these congruences of algebraic automorphic forms, arbitrary algebraic automorphic forms with others that are supercastable. So this will turn out to be very important for the application. And so what do we actually know about use construction? How general is this construction? So we know that if the prime p is very large, then Julie Kim showed in 2007 that actually all the supercastable representations arise from JKU's construction under the assumption that the characteristic of the field we work with is 0. So we work with a finite field extension of QP, not with the Dormant or a finite field. And and that the prime p is very large. I think I said that already. So the two assumptions, the prime p is very large and we are in characteristic 0. Under that assumption, everything arises from JKU's construction. But you might wonder actually what happens more general, what happens if the prime is not very large? And Mark Rieder and JKU, they gave a construction that is slightly different, and I circled this by yellow dots here. And the construction they gave, they called them the result of these construction epipelagic representations. Why did they call the representations resulting from the construction epipelagic? It's because the representation they constructed are those that are very close to the 0 depth. They construct a representation of smallest positive depth. And Mark Rieder, he thinks of representations as fish that swim in an ocean. And so if you move to oceanography, then the upper zone of the ocean, that's the epipelagic zone. So that's why he called these representations epipelagic. And so the nice thing about the construction is that the construction says, take a certain input, a stable vector in the Moy-Prasad filtration, something nice. Then they perform a construction, and the output are these epipelagic representations. And the input, they could show only exists for large primes. But in a joint work with Beth Romano, we could actually show that this input exists also for small primes. And I treated the general case myself also for small primes p. So we can actually construct new representations that do not arise from JKU's construction. So there's more out there to discover. And so the reason I'm pointing this out is because that's where this abstraction comes from, that my result with Sorgushin relies on the prime p to be sufficiently large. Because we have to first do more work for small primes p to extend it to all primes, which I hope is doable, but requires more work. On the other hand, JKU's construction allows us to get supercustal representations in a rather general setting. And so the most general setting is just to assume that P is large, but not to assume anything on the characteristic of the field itself. So that means if we assume P is large and this region here without any assumption on the characteristic of the field, we obtain that all representations arise from JKU's construction. So let me write this down as a theorem. So the theorem is that assume G splits over tame extension. That's because that's what JKU assumes. So for division units and division algebras, they become isomorphic to GLN over tamely ramified extension. So they are fine. And then assume that P doesn't divide the order of the Y group. So what is the order of the Y group? So for GLN, the order of the Y group is n factorial. So it means we assume that P is larger than n. And in worst case, for exceptional groups, we exclude the primes 2, 3, 5, and 7 in the worst case. Under this minor assumption, U's construction provides us with all the supercustal representations. And this is actually why in the work with Sarguchen, we assume that P is greater than the Coxeter number because that makes life easier. But it didn't work so hard to make the bound precise because there's really an obstruction here that has to be moved first. On the other hand, in this theorem, the obstruction is as good as it can get. I don't want to make this precise here, but in some sense, the obstruction is optimal. That means if P doesn't divide the order of the Y group, then we know everything arises from JKU's construction. And if P does divide the order of the Y group, when we are in the small region here, we have to work harder. We have to find a new construction. So why am I telling you about the exhaustion, even though all we want in the end is to have some supercustal representations for our global application? It's because the results in this paper, so the way I prove exhaustion, this actually crucially enters the proof to show my result with Sarguchen as well. So the methods used to prove exhaustion become very important to construct the supercuspidal types in the end that we need. All right, so let me see what time is it? All right. So let me say one more thing at this point. So that's the state of the art. That's what we are at. And I said we want to use U's construction. Well, there has been a small problem, which is that JKU wrote down a proof that his construction actually provides us with supercustal representations. And these are the ones we want to work with. We want to get these automorphic forms that are supercuspidal at a prime. But his proof that these representations are supercuspidal doesn't work anymore. So unfortunately, there was a typo in one of the references that he used. So a paper by Girardin was just missing a ±1, unfortunately. So it's from the time, I think, where you hand wrote your paper, gave it to a secretary to type it, and a ±1 dropped out. And so if you put the ±1 back in, the whole proof breaks down of JKU. So the main theorem that JKU relies on actually fails. There's a counterexample to it. So that was a scary moment. And I said, we want to use U's construction, so it better worked. So indeed, I first had to show that U's construction provides us with supercuspidal representation. So we don't have to worry, it all works out. So that's great. So that's now the state of the art. We have U's construction, which provides us with a lot of supercuspidal representations. And now having these supercuspidal representations at our disposal, we can go and try to construct automorphic forms that are supercuspidal at a prime. So how could we possibly do that? So for that, I like to move to the notion of types next. So what is theory of types? The theory of types is the idea that we obtain information about representations of our p-adic group G by studying representations of compact open subgroups. So for example, the type that we are particularly interested in for our global application is a supercuspidal type. What is a supercuspidal type? So a pair consisting of a compact open subgroup K and a representation rho of this compact open subgroup, a finite dimensional representation, is called a supercuspidal type if it detects supercuspidality. So what does it mean? It means that if we have an irreducible representation pi, and if this representation pi restricted to the compact subgroup K contains the representation rho, so that means this space of homomorphisms from rho to pi is non-trivial, then we want to infer that pi is actually supercuspidal. So in other words, a supercuspidal type is telling us if a representation tells us that a representation is supercuspidal if it's contained inside this representation. And so that's how we can detect a supercuspidality. And so then the theorem with Sorguchin, the next theorem, which is the local theorem that underlies the global theorem that I started with, is the following. Now, first in wake terms, I make it precise later. Assume that now the characteristic of our field f of our local field is 0. So for example, it could be QP, which is the one we need for global applications, and assume that p is greater than the Coxeter number. Then we construct enough sufficiently nice supercuspidal types to prove this theorem 1, to obtain these congruences between automorphic forms, between arbitrary automorphic forms and those that are supercuspidal at a prime p. So before I state the precise statement of this theorem, I want to give you a feeling for how do these types look like and how do these supercuspidal representations look like. So that's what I want to do now. Let's look at the example that G is equal to SA2 over our favorite field F, local field F. And I need a compact open subgroup. So let's take as compact open subgroup all the matrices inside SA2 that are on the diagonal 1 plus the maximal idea. In the off-diagonal upper right corner, it's maximal idea, and the lower left corner, it's the ring of integers O. And then I take as compact open subgroup this together with plus minus the identity for some technical reasons. And so I want to construct now a representation of this compact open subgroup that we can then compactly induce. So I want to construct a one-dimensional representation, so just a map to C star for you. How can we map this to C star? So the plus minus 1, let's just map it to plus minus 1. And each of you can choose your favorite character. There are two choices, the trivial one or the sign character, whichever you like. And now the question is, what do we actually do with this compact open subgroup here, with these matrices? So this is actually not just a random compact open subgroup. This has a name, which is called GX1/2. So what is that? What does the fun notation mean? So you have to start out with the Breuer-Tietz building. What is the Breuer-Tietz building? The Breuer-Tietz building is a lot of real vector spaces that are glued together that form a building, and then the group acts on it and encodes a lot of information, encodes compact open subgroups. So what it is in the case of SA2, in the case of SA2, this is just an infinite tree. So that's how it looks like. Where are the real vector spaces? So there are a lot of real lines. So here's one real line, here's another real line, and another one, and even more. So there are a lot of one-dimensional vector spaces, and the group acts on it, as I said. And now the interesting thing is that if we take a point inside the building, let's call that point X, we can look at all the elements that stabilize that point. So we can look at the stabilizer of the point X. And I tell you that if you look at how the group acts on that building, the stabilizer turns out to be all those matrices of the shape O's, O on the diagonal, O on the lower left corner, and P in the upper right corner. And I like to call the stabilizer also GX0. Why do I want to call it GX0? Because it not only stabilizes the point X equals 0, but also a ball of radius 0 around it. Well, that's just the point itself. The reason I like to say that is because now if you just stabilize the point, instead of stabilizing the point, you can stabilize larger and larger balls around it. So you can fix, say you fix the point of, fix the ball of radius 1/2, or a ball of radius 1.5, or ball of radius 1 or 1.5 or 2, larger and larger balls. And so if you do that, what you obtain is roughly the Moy-Poisson filtration. I'm lying slightly here, so precise definition is slightly off by some finite index. But so if you do that at depth 1/2, what you get is that the diagonal is slightly smaller, while the off diagonal stays the same. And actually all the groups in between are the same. So you could also say this is the same as depth 1/4, because it doesn't really matter if you fix a ball of radius 1/4 or 1/2. And so the next interesting thing is what happens at depth 1. At depth 1, now the diagonal stays the same, but now the off diagonal becomes slightly smaller. And you can keep playing this game and change the diagonal and the off-diagonal entries. And that's how you obtain the Moy-Prasad filtration. Instead of doing this at the point X, you could also do it at a different point, say at the point Y. If you did it at the point Y, you would just get the regular congruence filtration. So you got all the matrices that are congruent to the identity mod P squared, and so on. But Moy and Prasad observed that this is not the only interesting filtration. There are more filtrations. For example, this filtration here is another very interesting one. And in general, you get the Moy-Prasad filtration by having, say for GLN, you have the diagonal matrices where you have O 1 plus P squared, and then you have the off-diagonal entries where the jumps, where you jump down from O to P squared, and so are determined by the point in the building that you choose. And so that filtration has a lot of nice properties. And this is actually the filtration that is used in JKU's construction a lot. And so one nice property is that all these groups are normal subgroups, and the quotients here are nice vector spaces over the finite field, and the zeroth quotient is a finite group, finite reductive group. And so what happens now, what we can do is we can just mod out by the next filtration subgroup. I now write it as 1/2 plus, which is just the next one you have seen. So this is the next filtration subgroup. And what happens is that this is actually just isomorphic to the anti-diagonal, how do you call it? The matrices that have entries only on the anti-diagonal under addition, where the entries are F2, the residue field, because it's just O mod P. So now we have mapped down this big compact open subgroup to just some finite group. And what do we do with such a matrix? We can just send a matrix AB to the sum A plus B, which is an element of the finite field. And now the finite field we can just map to C star by some non-trivial character. So for example, if it's FP, we can map it to the P's roots of unity. Then if we take this composition here, this is the character that I like to call rho K tilde. So in this way, we now obtain a representation of this compact open subgroup, and we obtain a supercuspidal representation now by just compactly inducing this representation. So what is the compact induction? It means we just take, as for normal induction, all the functions on the group G, mapping to the complex numbers, such that K in our compact open subgroup pulls out on the left via this character rho sub K tilde. And compact induction means that the function should be compactly supported. So this is a huge space, an infinite dimensional vector space, roughly the space of functions on G mod K tilde, and the action on it is just via right translation. And so this is actually a supercuspidal representation. It's even one of these pelagic representations. And so what are types now? So in that setting, a type could be just that you take this compact open subgroup K, so you forget the plus minus 1, and take this character on this compact open subgroup K, so you forget how this plus minus 1 act. This is a supercuspidal type because if a representation contains this representation rho when restricted to K, then it's one of the two representations constructed above here. One of the two choices for this character on plus minus 1. You could either use the trivial one and get a supercuspidal representation, or use the non-trivial character, and you detect supercuspidality. But this type doesn't tell you which of the two representation it is, but it tells you it's one of the two. In general, JKU's construction becomes much more complicated. Instead of just the character, you will have a much more complicated representation there. You don't just start with one Moy-Prasad filtration subgroup, but you start with the whole bunch of Moy-Prasad filtration subgroups for subgroups of the original group. So you take a so-called twisted Levy sequence, and for each twisted Levy subgroup, you take a Moy-Prasad filtration subgroup. And then on each of these subgroups, you take a character, and you also take a depth 0 piece, and then you put everything together in a complicated way. And in the end, you end up with the K tilde, which is the very large compact open subgroup, together with the representation rho K tilde, which is very complicated. It's not a character anymore. It's only a character in this particularly nice setting here. And what we actually want to do is, this is very complicated, but for global applications, we want our supercuspidal types to be still characters, to be particularly nice. And that's where the difference between the representations and the types come from. All right, so let me move on to the types now. I hope you can keep this example in mind just so that you have seen a supercuspal representation. So let me recall this. Supercuspal type, I said before, with some compact subgroup with a representation that detects supercuspidality. So that's just the definition I've shown you before. But now for our global applications, we want a slightly different version, and I call that an omni supercuspal type. Maybe before I show you the definition, because it's a bit scary, let me repeat what I said earlier. So if you construct supercuspal representation via use construction, the K is huge usually, and the representation are very difficult. What we want for our global application, we want these compact open subgroups to become smaller and smaller and smaller, because I said we want to capture automorphic forms of arbitrary level. So we want this K to be smaller and smaller. And another thing is that we want this representation not to be complicated, but we want it just to be a character. That's much more helpful for global application. So the difficult part now is to move from knowing how these supercuspal representations are constructed to extract some compact subgroup that becomes smaller and smaller, and a character that already determines supercuspidality. On the other hand, we lose that we pin down the supercuspal representation. We won't be able to pin it down anymore, but we just want to find some supercuspal representation. And so the notion of omni supercuspal types is made slightly more stringent than what I just said. It's made in a way that we can actually obtain the global application. And so it says the following. What is an omni supercuspal type? It is a pair consisting of a compact open subgroup U, which is the one that will get smaller and smaller and smaller. And lambda, what is lambda? Lambda is now a map from U to not the complex numbers, but to Z mod P to the MZ. And this is this P mod M that comes from the congruence mod P mod M that we want to construct congruences with respect to. And it should have the following properties. If we now compose this lambda with an arbitrary non-trivial character from Z mod P to the MZ to the C star, so an arbitrary complex character. So we obtain this composition psi composed with lambda, lambda composed with psi. We want this to detect supercuspidality. So we want this pair U, comma, lambda composed with psi to be a supercuspal pair. So every representation that when restricted to U contains lambda composed with some non-trivial character should be supercuspal. And as I said, this is made precisely to have the global application. So that's why it might sound a bit complicated. And so then the precise result is now the following, joined with Saugeshin. Assume that, again, the characteristic of our field is 0 of the local field and P is greater than the Coxeter number. Then there exists explicitly constructed sequence, UM lambda M, such that these UM lambda M's are omni supercuspal types of level P to the M. And these compact open subgroups U sub I, U sub M, they are becoming smaller and smaller and smaller. So they form a basis of open neighborhoods and they are normal with each other. All right, so that's the statement. And we have, I said it's explicit, so we have some control over how they look like, how these representation look like, for example, under the local Langlands correspondence. All right, so that's the abstract statement. Let me show you an example of how these omni supercuspal types look like. So, for example, if we look at SA2 over QP, and say P is congruent to 3 mod 4, so it's in particular greater than 2, then as compact open subgroups U sub M, we can take the congruent subgroups. So all these matrices that are congruent to 1 mod P to the M plus 1. So that definitely becomes smaller and smaller and smaller. And as our lambda M's, we can just take the following. So we take an arbitrary matrix in UM, so that's just of the form 1 plus A P to the M on the diagonal and 1 plus D P to the M on the diagonal. And the off diagonals are inside the maximal ideal raised to the M plus 1 power. So they are of the shape P to the M plus 1 times some variable B and some variable C. And we send that matrix to just the difference between C and B, so C minus B, mod P to the M. So this map here is definitely a surjective. So this map here is definitely a surjective map. I just got a question. Why do I suppose that the characteristic of the field is equal to 0? And this is actually right now the answer that I'm telling you. It's really crucial to assume that the characteristic is 0 because we want these map to surject on ZP mod p to the m ZP. And that only works if we are in characteristic 0 and not if we are in characteristic p. And so this map, so it surjects definitely. And this is actually just, it's a character, because if you multiply two matrices here, it corresponds indeed to the corresponding addition here. You can work that out. That's precisely because I've chosen this matrix to be so deep down in the filtration. And by looking at it mod p to the m, all the error terms cancel out. All right, so that's an example of omni supercuspidal types. So are there any more questions in the chat? I just saw a private question that I answered. Any more questions at that point? All right. So let me now give you an idea of how can we use, just checking. I started at 12:30, so I think I have 15 more minutes roughly. Someone should object.
Yeah, that's correct. Yeah.
Okay, good. So that's the theorem for the existence of these omni supercuspidal types. And I said that's precisely what we need for the global application. So let me now tell you, how do we obtain the global application from that? So how do we go from this theorem 4 to theorem 1? So I recall theorem 1 was this statement that there exist these compact open subgroups with this representation so that we obtain the congruence of arbitrary automorphic forms with automorphic forms that are supercuspidal at a prime t. So here's the idea of the proof. We take as our compact open subgroups, well, what else can you take other than the omni supercuspidal types that I've just introduced? So as these pairs, we take as UP m lambda m, we take omni supercuspidal types of G of QP that come from the previous theorem. And we take them so that these compact open subgroups are sufficiently small to avoid any problems. So that's the compact open subgroup, that's the UPM. Now I have to tell you what representation sigma here we take, what action on the ring AM. And we take the following action, so let me walk you through it. So we have a map from UPM to Z mod P to the M, that's just our lambda M. And now I want to map this to AM. So let me recall AM because it has been a while since that popped up. So AM, this was the ZP where we attached all the roots of unity that are non-trivial, so or to the p to the m roots of unity. So we took power series in T mod out by this polynomial that corresponds to attaching all the non-trivial p to the mth roots of unity. And so how can we map now an element, say n mod p to the m to an element in am star, the invertible element? We just map n to t to the n. So that means the image here will be just the powers of t. And now how can we act on AM? We just act by multiplication. So we have now an element in AM star, and we can act on AM by multiplication. So in other words, we send an element A to A times the identity. All right, so that's the sigma M. And I claim that this actually solved the problem. So why does it solve the problem? Oh, I didn't mean to, sorry. Why does it solve the problem? Let me use the eraser. So first of all, condition 1, well, that's definitely satisfied because that's how we construct the UPM. We constructed them to be decreasing and normal. So the second is now we want this congruence between these algebraic automorphic forms and those AM coefficients. So in order to observe that this is true, we already observed that Z mod P to the M is congruent to AM mod 1 minus T. So that's what we observed earlier. And I said that the result follows if we just have a trivial action on it. But now my claim is that sigma M is actually acting trivially on this quotient, because what's the action of sigma M? The action of sigma M is multiplication by T to the M. But now T to the N, T is equal to 1. So it corresponds to multiplication by 1. So that's the trivial action. And then if you believe me that you can pull in the P to the M and 1 minus T here, you just literally obtain the same objects, just these functions on these double cosets, because the action of sigma m becomes trivial. So the real tricky part is to see the third property, that all the automorphic representations that appear on the right-hand side are now supercuspidal at the prime p. How do we see that? So what are the coefficients? We have am tensored with qp bar. And so that's isomorphic to just the product sum of qp bars for I ranging between 1 and p. Each sum and corresponding to a non-trivial root of unity. So in other words, if we map am inside this tensor product, it corresponds to mapping it in this sum as follows. We take an element t and map t to the some chosen root of unity to the i's power in the i's coordinate. And so that's the coefficient. So that means now if we look at our automorphic forms with...
Oh, I think you want the p to the mth root of unity.
Oh, thank you. P to the mth root of unity. Yes.
And also I runs onto p to the m.
And I runs from. Thank you. Thank you. And so what is now the space of automorphic forms? The space of automorphic forms now decomposes the same as a sum over all these. So let me copy this. Our level with coefficients now in where we sum now over all the qp bars. And now the question is, the question is, what is the action of sigma on these spaces? And so the action I claim of this compact open subgroup UPM via sigma, this acts on the space here, on this copy of qp bar via, let me call this chi I composed with lambda m, acts via chi I composed with lambda m on here. And what is chi I? So chi I is just the map that sends, or maybe let's see, what is the action? So we said that sigma m, the action is via this composition. So that means we take first we take lambda m, and then we take an element n mod p to the m to send it to t to the n, and then we multiply by t to the n. But now t gets mapped to the p to the m's roots of unities to raise to the power I. So that means what we get on this summand is just this composition. So it means we compose lambda m with the map that sends n mod p to the m to the p to the m's roots of unity raised to the i's power times n. And so that's, in other words, this means we sum here over lambda composed with all these chi i's, where chi i's, they are non-trivial characters. So in other words, that means, oops, and I'm missing a bracket. So that means, sorry if this got a bit small, that means that the action of this compact open subgroup UPM is via lambda m composed with a non-trivial character. And now we call what was an omni supercuspidal type. An omni supercuspidal type said that if a representation restricted to UPM acts via lambda m composed with a non-trivial character, then the representation we started with is supercuspidal. So that means we conclude that all the representations that occur in this space here are actually all the automorphic representations that occur in this space, which have then therefore the property that UPM acts via one of these characters, have to be supercuspidal at the prime p. So that means we obtain the result. All right, so that's how we obtain theorem 1 from theorem 4, how we use the local result to obtain the global result. But so the real beef of the, how to say, the real input really lies, or the real new input lies in the local result theorem 4. So I want to use the last 5 minutes to tell you a bit about the local result. So here's a sketch of the proof, but it's a sketch of the outline of the proof because that's all I can do in 5 minutes. So now we're back to the local setting with our p-adic group, and we want to somehow construct these omni supercuspidal types that then give us the congruences. How can we do that? So first, we assume that G is adjoint absolutely simple. So just think of your favorite group where the center is trivial. We can reduce to that case. The first step, so it's a two-step process. The first step is that we construct omni supercuspal types from a nice input, and we call this nice input zero-to-all data. So what are the zero-to-all data? So let me try to give you an idea. So I talked to you about JKU's construction earlier, which is this construction, this most general construction of supercuspal representation known today. And it starts with some input. So we have some input, use input. This input is rather complicated if you see it the first time. It's a sequence of subgroups called twisted Levy subgroups. And for each subgroup, you have a character, a nice character of some depth. And you also add a depth 0 piece to it. And I outlined earlier that this then all gets put together in a big representation of a big compact open subgroup. So once we have the input, out of that, we get some compact open subgroup K tilde, some representation row of K tilde, such that if we compactly induce this representation, we get a supercuspal representation. So that's what use construction did. And now for the omni supercuspal types, we want to take some subpart of the data, which we call zero-to-all data. And these zero-to-all data, they are much easier. So what are they? They consist of torus. So T is a maximal elliptic torus. Maximal elliptic means compact torus. So for example, inside SL2, we can embed the norm 1 elements of a quadratic field extension of our field that we work with. That's a maximal elliptic torus. And we want to take a real number. So R is some positive real number. And then we have a character phi. So phi is a character, a nice character of our torus, which has the depth R. And so out of these zero-to-all data, which is somehow, it's a bit like a skeleton of used input, just a skeleton, or even less than a skeleton. Out of these data, we then construct the omni supercuspal types, U sub m, lambda m, omni supercuspal types. And what are these? So this U sub m is a subgroup of K tilde, because I said K tilde is rather large, and there's no way that K tilde becomes smaller and smaller and smaller. It's always rather large. So these U sub m are small subgroups inside there. And this lambda m, in some sense, is contained in this rho sub K tilde. So if you restrict this rho sub K tilde to the compact open subgroup UM, you encounter this character lambda m. And so then the difficult part was to show that if you have such a pair U sub m and lambda sub m, which can, if there was time, I could define for you explicitly, so it's something you can write down explicitly, that once you have such a pair, it actually is an omni supercuspal type. That means that every representation that contains it and contains lambda m composed with some arbitrary non-trivial character is actually supercuspal. And that relied a lot on arguments that I had in my exhaustion proof earlier. So that's the first step, to say we reduce the problem to finding zero-to-all data, and we show that this is actually enough. And then the second step is, well, we have to construct enough of these zero-to-all data. And well, in order to construct zero-to-all data, let me go back, we have to find these maximal elliptic tori and these nice characters of it. So that requires to understanding how elliptic tori look like, to work with the structure of the Y group, work with the Moy-Passat filtration to construct then these nice characters, and it uses a lot of structure theory of these groups in the end. So that's the second step. And well, once we have enough zero-to-all data, we obtain then these omni supercuspal types, which allows us to obtain the global application. All right, I hope you got an idea of the rough state of the art of the representation theory of p-adic groups, and as well how we can use these to obtain global results, and how all of that is actually just making explicit a remark of a paper by Peter Scholze where he said, wouldn't it be nice if this was true? And it is true. All right, let me stop here. Congratulations, Peter.
Thanks.
We have questions for Jessica?
Okay. So my first question was, so we had the story, this construction of U, which somehow works for somehow if it splits over tame. So is there some story that also works for a non-tame case?
That's an excellent question. So use construction only works in the tame setting. And so are you talking about the group being, maybe let me first ask, are you talking about the group being split over tame extension or the setting being tame itself?
Whatever the inputs were in
okay.
I'm not quite sure what they were.
Well, so let me answer both questions. So some people say that setting is tame means P doesn't divide the order of the Y group because then all the tori are tame. So use construction only can handle tori that split over a tame extension. If you want to go to the wild case for GLN, we know it for all primes P, so Bushnell and Kutzko also know how to deal with wild tori. So there you see a first example of a wild case, but it's getting much more complicated. If you want to look at general, so first of all, tame groups where you include also small primes, or if you look at in general groups that do not even split over a tame extension, much more work is needed. And a lot of authors are scared of that setting, so not much progress has been attained yet. That's what I'm currently working on. So I hope that at some point I can give you a better answer than now. At the moment, what I can tell you is that I talked about these epipelagic representations, the one constructed by Rita and you. And the nice thing about their construction is that they don't assume that the torus is tame, and they don't have to assume the group is tame necessarily as a consequence either. So together with the input that I showed that actually the input for Rita and use construction exists for small primes, this allows us to get some representations in the non-tame setting there for rather general groups as well. But they are only of smallest positive depth, so they are only epipelagic. I know that you can get some more representation deeper down in the filtration, so representation of deeper depth, but so far that's just on scratch paper. So it's definitely much more complicated. I can actually, no one ever asked me, the starting slide of my presentation shows you why it's so much more complicated, because one reason is that the building doesn't behave nice under wild extensions, but that's only one problem that occurs. So the short answer is it's work in progress. There's a lot we don't understand yet.
Okay. I have another question.
Okay.
Namely,
actually, could you tell me who you are, because the picture is so small I can't even see.
Yeah, I'm Konrad.
Okay.
Right, so you defined the notion of supercuspal type. Is it clear that they exist even at all? Or I wasn't quite sure whether it's even clear that there is any supercuspal type.
Well, I mean, we proved that there are plenty of supercuspal types.
Sure, okay, but I mean, your proof is probably work, right? There's probably some non-trivial input in there. So I was wondering whether there's...
So it's an excellent question, because it leads to actually a lot of interesting questions. So there's another notion of types, which is more general, and more specific in both directions. So there's the idea of that you can decompose your category or smooth representation into Bernstein blocks. And then the question is, are there compact open subgroups with representation that single out these Bernstein blocks? And these are also called types. And what I call by supercuspal types are types corresponding to supercuspal blocks, but not necessarily to one, but to a bunch of. And so okay, several answers to your question. So if you want to study types, and for generality, all the results I talked about for supercuspal representations also work more general for types. On the other hand, that then also means that, so if P doesn't divide the order of the Y group, the group is tame, we know all types, that the types exist for all Bernstein blocks. So we know in particular there are supercuspal types, which are just the same, more or less the same as these the construction of representation via compact induction. For more general groups, we don't. It's an open question. It's an open question how to construct supercast representation, and similarly, I think it's an open question also how to construct types in a more general setting, and the same how to construct then supercast types as well.
Okay, thank you.
Sorry, I don't know if this was an answer to your question, or was your question aiming for something?
No,
else?
I think I understand somehow what's going on roughly.
So basically, the big picture is, if we are in the chain setting, P doesn't divide the order of the Weyl group. We know everything, and outside that setting, unless we are working with special groups like GLN, we don't know yet if compact open subgroups tell us everything. But the folklore conjecture is that compact open subgroups with representation should tell us everything, because the folklore conjecture says that all supercuspals are induced from compact open subgroups.
But maybe for your, I mean, you also asked whether it's somehow clear that supercuspal types exist, and that I don't think it's clear, because it implies that supercuspal representations exist, and this, I think, for a general group was some kind of open problem back in the day.
Yeah, so that was actually, well, that surprised me. That was open until recently, because I thought we know it, but I guess no one actually sat down and checked it, because
No, I think it was.
So that's a good. So we know now that, so Berzaplis showed that in the case that the characteristic of our local field is 0, then we get supercuspal representations for all groups. So every group admits a supercuspal representation, which is the same way how he gets omni supercuspal representations in general, basically, roughly speaking. And we know it also for also in the general case for equicharacteristic fields. I think that's work of Adler and Mishra recently, and that's really recent. And I was very surprised that it wasn't known before that. But basically, no one sat down and said, "Okay, we have these explicit construction. Let's check that the input is non-empty." That's basically what you need to do, and what people hadn't done before. So yeah, we know that supercuspal representations exist for all groups. So there are also some supercuspal types. We just don't know how much we get out of it. Thanks, Peter. So do you want to add more, Peter?
No, I don't want to add more. So other questions?
All right, any further questions? Because that's been quite a lot of questions already. So, oh, I see there's one in the chat.
Oh, my friends just said it's known that supercuspal representations exist, which is what I just explained.
Oh, great.
So they exist, and well, they exist also mod L and mod P. That's a whole different world then.
All right, so let's wrap it up there. Thanks everybody for joining today. We'll pick it up tomorrow again.